Welcome to Mastering and Guideline in Ultrasound and Echo. Hi everyone, we have another multiple choice question. First, in an adult with height of 180 centimeter, we measure blood pressure at the left arm at the level of the heart with 120 over 80 millimercury. How much will be pressure on the ankle when the patient lay down flat or supine and when stand? 120 over 80 and standing 210 over 170, and B 120 over 80 doesn't change at both situations the same. C 210 and over 170 and standing is the same, and the last choice is 120 over 120, 80 over 80. As you know, on the earth we have a force we call gravity. If we have a column of the here blood and has a height of 130 centimeter, that is almost equal the height of the heart from the ground. At the bottom, the pressure, if we measure it, it will be around 90 to 95 millimercury. Some references take it as 100, but 95 millimercury. In other words, the blood, because of gravity or weight, has a pressure around 95 to 100 millimercury. Since the pumping and circulation system has itself a blood pressure, so pressure at the ankle will be combining of the hydrostatic pressure plus the circulation system pressure based on the diastolic and systole. So on the standing will be around 210 and the diastole will be around 170. So the right answer is for the standing is this one. What about lay down? Lay down, the hydrostatic pressure at all level almost is the same. So the blood pressure at the ankle when the patient is lay down and supine almost is the same. It doesn't change. As general rule, when you they give you such question, take the hydrostatic pressure at the level of ankle around 100, around the lower thigh 45 millimercury. That's enough because we are just dealing with these two type of the measurement. Another tip that you have to remember, at the tip of the head, because the height from the heart to the head is almost 50 centimeter, so something like 40 millimercury pressure at the hydrostatic pressure is lower than the level of the heart, and as a result systolic and diastolic the same amount will be less than the blood pressure at the level of the arm. As the same concept, you know, the astronauts when they go to the space, because there is not gravity, they will have some changes in hemodynamic, especially on brain and other spot, because in all position there is lack of the hydrostatic pressure. Another important point that I want to mention here is the differences between the venous blood pressure and arterial pressure. In any situation, the flat, supine, or standing, The amount of hydrostatic pressure that apply to both arterial and venous is the same. In other words, the differences pressure between the systemic venous and arterial pressure is almost constant, and it will be around 85 millimercury. We call this pressure differences driving pressure or pressure gradient between arterial and venous pressure. That is almost always in all position is constant and doesn't change. Next one. In a normal patient, if the TV inflow be 50 milliliter, how much will be left ventricle and right ventricular stroke volume? As a general rule, in any closed circuit system, whatever comes, it goes the same amount. In any spot of the heart, if we don't have any regurgitation or shunt, at any location, the amount of the blood come there, the other spot is the same amount. So if 50 milliliter goes to the through the tricuspid, the same amount go to the pulmonary, the same amount come to the LA, to the LV, and to the aorta. So the answer will be 50-50 dozen. From the same aspect, we use continuity equation. What does it mean? If we measure amount of the blood passed through this area, we can measure the amount of the blood passed through to the LVOT or aorta. Just how? With the continuity equation. Continuity equation, we go measure, for example, here, mitral valve area, multiple mitral valve VTI, that we do continuous Doppler on the mitral valve and trace it. On the mitral valve area, we go measure diameter, and based on the math formula, 0.785 multiple diameter power 2, it calculates the stroke volume. And it will be equal the same stroke volume for the, for example, here LVOT. Just we measure LVOT area, multiple VTI of LVOT that we do with the pulse Doppler in apical 5 or apical 3. With the same, again, aspect, we use it for the continuity equation for calculation aortic stenosis, how much aortic valve area will be. With the Doppler and 2D, we can measure all these three parameters. When we measure all these three parameters, finally, machine or ourselves calculate aortic valve area, and based on that, we can grade stenosis. Now, another question. In a patient with MR, just MR, not AR, not shunt, just MR, following parameter has been measured. And the diastolic volume 100 milliliter, stroke volume 50 milliliter, mitral valve inflow volume 70 milliliter, heart rate 50 beats per minute. First, how much will be MR? And second, in above question, how much is end-systolic volume, EF, and cardiac output? You add another question, cardiac output. Okay, let's go. In this such question, when it goes in the board or anywhere, always first draw a diagram of your parameter and finding. Here, for example, apical plaques view. We have how much it goes, and the diastolic volume means that the maximum the blood goes to the left ventricle at the end, it will be 100 milliliter. And amount of the blood goes, stroke volume, the definition of stroke volume is that amount of the blood with each beat, or each beat goes to the aorta, is 50 milliliters. So 50 milliliters goes to the aorta. And mitral valve inflow, the amount of the blood goes to the left ventricle. Now we can see 70 milliliter came in, but only 50 milliliter went out. It's very easy, simple. We can say MR. So only from the 70 milliliter, only 50 milliliter gone. So what happened to the 20 milliliter? 20 milliliter go back to the LA. So the amount of the MR is 20 milliliter. Now, from that, how much will be a stroke and systolic volume? We have two ways. How much blood it was there that we add 70 milliliter, it become 100. So 100 minus 70, 30 milliliter. Very easy. And based on the definition of ejection fraction is end diastolic minus end systolic divided end diastolic multiple 100%. So 100 minus 30 divided by 100, ejection fraction will be 70%. In other words, in a patient with MR, they have very hyperdynamic heart. Even the output is not too much. That is one of the reasons this type of patient with the significant MR, they have lack of energy and shortness of breath beside of the pulmonary congestion, because cardiac output decrease. 20 milliliter of this, that is a lot, go back, doesn't go forward. So that is the difference between if you want to calculate it based on the stroke volume or based on the real ejection fraction will be different. Don't use stroke volume divided by that. Use end diastolic minus end systolic. That is correct definition for calculation of ejection fraction. And final, how much will be cardiac output? Cardiac output definition is how much blood goes to the aorta, systemic circulation in each minute. So we multiple stroke volume multiple to the heart rate. 50 multiple 50, 2,500 milliliter per minute will be your cardiac output. Don't forget, if you have any question, ask in comment. Up to next time.